Hey everybody, welcome back to our last session of the annual Cementing Leaders Forum. I want to say thank you first for calling in and participating with us. We have a live Q&A at the end of the session. After the live Q&A, we're going to have some closing remarks from our Vice President of Cementing, Jim Collins. So please stick around for that. If you missed our morning session, we covered the topic of cementing's digital transformation. This session is going to be on sustainability and cementing for the life of well. So without further ado, I'm going to hand over to Siva for his presentation.
Hello, good morning, good afternoon, and good evening, ladies and gentlemen. Welcome to the last session of Cementing Leaders Forum 2021. My name is Siva. I'm a principal engineer with the R&D division of Cementing PSO. In this session, I'm going to provide you an overview of the features Halliburton has been developing in the space of life of the well cementing. I'm sure many of you have interacted with our engineers the process of designing cement systems that last for the life of the well using our flagship analysis tool, Well Life. The features that I'm going to cover here are part of the larger framework of the Well Life analysis. Specifically, these are the three features I'll be providing an overview on. The first is the upgrades that we have made to Well Life 6.0. Specifically the science part of the upgrades. This was released on 17th September and is now available for all our engineers. The second feature is on how we model integrity of plugs, although it's mentioned as plug-in abandonment. Really, the example in the workflow defined works for all kinds of plugs. The last feature is more work in progress within technology, but the idea is to give you a glimpse of what we are trying to do as far as design considerations for CO2 storage are concerned and invite some feedback and inputs from you. Let's look at each of them. Specifically on the cement stress state. This was the improvement we have made in Well Life 6.0. Shrinkage and expansion, as you all know, are one of the principal load factors that affect the stress state of cement. And when you do an analysis of the kind of well life using a finite element framework, you can see that this casing, cement, and rock interact with each other. So essentially, the stress state of the cement is a function of the properties of the casing and the rock as well. And any effect of constraints in the form of difference in stiffnesses of the materials, difference in the geometries, and loads is already accounted for during the analysis. What that means is that any measurement method that we use to provide an input to the well life analysis should not impose any additional constraints. However, the angular ring test, which is recommended by the API, is known to have providing additional constraints during the measurement process. If those constraints are not discounted for, there is a risk that the effect of shrinkage or expansion on the cement stress state is either over penalized or under penalized depending on the circumstance. Let me explain a bit more what I mean by the additional constraints coming from measurement. If we dissect the ring mold, this is how it looks. There is an inner ring that's very stiff relative to the stiffness of the cement. And then there's a top plate that is bolted. Now imagine the cement is trying to shrink radially during the measurement process. By virtue of being a ring geometry, it tries to go radially inward. However, the stiff member, the inner ring, would inhibit any radial shrinkage or radial inward movement in this case. Now let's look at expansion. When there's a possibility of expansion, the outer ring, which is flexible, would allow for an expansion to happen with practically not much of a constraint. but the top portion of the plate, which is now bolted, would not allow for an axial expansion to happen. So in essence, it is constraining some of the potential for axial expansion. And as a consequence, if you can imagine, mechanically speaking, by virtue of Poisson's ratio, there will be more amount of radial expansion than what it was otherwise. So this way, depending on the constraints that are exerted at different stages of hydration of cement, and also depending on whether it shrinks or expands, it's possible that we are not representing the right value of the measurement, the free body measurement. So what can we do about it really is, the good news is that we can use numerical analysis to replicate an actual ring mold experiment on a finite element framework. And when we do that, we will be able to derive the relationship between what the free body shrinkage expansion is and what the constrained shrinkage expansion is that you'll observe in a ring mold. It is the free body shrinkage or expansion that matters, that should go into the analysis. Because, like I said, the analysis is automatically taking care of the effect of constraints. Now, here is the representation of the different boundary conditions for the case of shrinkage and for the case of expansion that will be exerted on the ring geometry of the cement during an angular ring test. So what we did was we performed a series of ring mold test experiments numerically by giving different values of free body inputs and measuring what are the observed outputs of shrinkage and expansion in a ring mold. As a consequence of that, we were able to build what's called a calibration curve here. We are looking at Poisson's ratio on x-axis, because if you were to imagine, Poisson's ratio connects strains, or in other words deformations, along different axes. And because of these constraints, the amount of deformation that happens in an axis is a function of the Poisson's ratio and the constraint in the other axis. So that's why only Poisson's ratio appears as a property of interest that controls the effect of constraint, not Young's modulus. And on the y-axis, you're looking at two strains. The numerator is unconstrained strain, which I'm also calling as free body strain, which is what has to go into as an input into the analysis. And the denominator is the ring mold measurement that a lab technician would observe when they're performing the experiments. Armed with this kind of a calibration curve, when an engineer inputs a ring mold measurement into the well life input screen, the calibration curve would be used in the background to produce or calculate the unconstrained strain, which then goes as input into the analysis. That's how we are able to overcome the risk of either under-penalizing or over-penalizing the cement stress state because of a gap in how the shrinkage and expansion measurement is happening in presence of constraints during the measurement itself. So here is the input screen that you will see in WellLife 6.0. The user will define the number of molds that are used to measure to get a good statistical behavior. In this case, there are 3 molds. There'll be initial reading for each of these molds, which we are calling initial micrometer readings. And then there'll be a time dependent measurement. In this case, it happens to be day 1, 3, and 7. And of course, the test temperature and the measurement temperature and the readings themselves. So all of this data will be internally processed to obtain the denominator, which is the ring mold measurement strain. And that in turn will be used in the calibration curve to get to the numerator, which is the free body strain. And any stresses that are generated in the cement as a consequence of this free body strain are what are being calculated in WellLife 6.0. So this is how we have worked on improving the stress state of cement by relying on an API recommended test method and further overcoming the constraints offered during the measurement itself. Now let's look at the second feature, which is about considerations during cementing for the plug and abandonment in general for any plug. Now, when we say what kind of loads will the plug will experience, it really can be a broad question. What we try to do here is create an example for you to show what kind of analytical capabilities are available at your disposal. So I'm showing you a portion of the entire wellbore and specifically 1/2 symmetry in the axial direction. So imagine that only half of the plug is being shown here. The other half is a mirror image on the left. You can see the casing in black, the annular cement in gray, which is different from the plug cement, and the formation. Although the thickness of the formation shown here is small, this is not drawn to scale. So technically, when we did the analysis, the formation radial extent was large enough such that we can apply in situ boundary conditions on the farther edge. These are the potential load scenarios that a cement plug can experience. Are these all? Not really. These are some of them. Like there could be hydrostatic from the spacer or mud above it. There could be a pressure test that happens once the plug is set. Potential drilling loads, if it's not an abandonment plug, let's say it's a kickoff plug. The shrinkage and expansion driven stresses itself coming from within the plug. And a potential production from the bottom of the plug. Maybe because the reservoir is building pressure over time, or there's a neighbor well that was fragged and there is a communication to this well and there's a buildup of pressure below the plug. So these are some of the potential loads that the plug can experience. Along with this, there are loads that the cement sheath will experience coming from the pore pressure of the formation, which are not shown here, just to keep the graphic simple. Additionally, there are also temperature loads because the formation far field is at in situ temperature. The temperature inside the casing or in the plug is close to a circulating temperature during placement. And over time, the temperature equilibrates. So that process is also modeled in the example that I'm going to show. What happens under these kind of load scenarios? These are the potential risks to the cement plug, specifically to the integrity of the cement plug. There could be a potential mechanical failure, like the case of shear failure, tensile failure that we typically model in well life. Those are driven by excessive compression stresses or excessive stresses in the tension. There could be debonding between the plug and the casing. If this is a scenario of an open hole plug, there could be debonding between the plug and the rock. That's also doable. In this example, I try to create a context where you have annular cement also, just to be able to show that all potential possibilities can be captured. The third potential failure mode, I don't know if I can really call it a failure, but really a potential for flow path is through the permeable portion of the plug, which is specifically driven by what's the permeability of the plug, what's the differential pressure across which the plug is set. These are the failure mechanisms that can be investigated from an analysis. And we can ask whether there is a risk of failure in any of these modes specifically. Now, if you have noticed, by virtue of being an axial geometry, we can conveniently analyze the effect of radial loads coming from the formation in the form of pore pressure in situ stresses and the axial loads coming from the bottom of the plug or the top of the plug. If it were a 2D plane strain model on a cross-section cut, this kind of analysis would not be possible. So by virtue of being able to look at the response of the plug as a whole, it's imperative to be able to look at an axisymmetric model or a three-dimensional model if the computational complexity is manageable. So what do we really do when we say the word integrity of plug? We can, in essence, answer two questions. What kind of mechanical properties are appropriate for the plug? I gave some examples here: Young's modulus, Poisson's ratio, strength, it could be permeability, it could be tensile strength. And second, what should be an acceptable length of the plug from a long-term integrity standpoint or from the stress propagation standpoint? These are the two questions we can potentially answer by an analysis of this kind. This is the example scenario that we were trying to model. And like I said, axial and radial loads are critical. The bonding characteristics should be modeled. Let me explain what I mean with the inset here. Take a well of this nature. Like I said, I'm looking at 1/2 of the symmetry, which is why I'm calling it an axisymmetric model. Here is how the scale down model looks like. It's important for me to highlight that when I use the word scale down model, I'm not reducing the length of the plug whatsoever. I'm still considering the entire plug. What I'm in essence doing is removing all of the overburden above it and compensating it with some effective height so that the temperatures, stresses, all the three directional stresses, vertical and both the horizontal stresses, exerted on the top of the model of interest, which is the unshaded portion, are still correct. Because really it doesn't matter what happens above it when the focus is on the plug. However, the effect of the weight of the overburden and the thermal gradient of the overburden is still being carried into the model. That's what I meant by the scale down model. If the plug were say 250 feet, this would be 250 feet in the graphic that you see. Now, coming back to the bonding characteristics, there are different ways for us to treat the interfaces, either as elastic interfaces or as a nonlinear elastic interfaces, or using some kind of a slip or a friction driven by some form of a shear bond. So really all kinds of possibilities exist at our disposal to be able to model the interface. The specific type of model to use is a contextual question and can be dealt on a case-to-case basis. And we have, in this example, we have applied the loads coming from the formation, which is the pore pressure load and the overburden stress. And we have applied the hydrostatic of the spacer above. And we have applied pressure from below, simulating a potential scenario of a buildup over time. So like I said, the model size should be computationally manageable, yet you cannot really scale down the size of the plug because the boundary effects would propagate deep into the plug and the assessment that you get for the length of the plug would not be appropriate. Let's see the results of this particular example case. If I can focus on the right in terms of what are the load stages being applied, there is a placement part where there's pressure above the plug, which is hydrostatic, and then there is a radial pressure coming from a depleted pore formation. And then there's a weight on plug. During weight on plug, there's a temperature evolution. The plug itself is going from circulating temperature to the in situ temperature over time, and there are radial gradients of temperature, by the way. And there's a shrinkage and expansion within the plug. And when I say the word life of the plug, we are simulating a potential case of pore pressure building over time. Is that the only thing that changes with time? Not necessarily. Can we simulate any other potential loads changing with time? Absolutely. It could be pore pressure from the bottom, it could be temperature of the plug, drilling loads from above, the pressure exerted by the formation on the cement sheath itself, if it's a cased hole plug, or directly on the plug if it's an open hole plug. Although there are multiple different properties of significance, I'm highlighting those that are primary in nature, which is the Young's modulus and Poisson's ratio here, of each of the material that I've considered for this example. And you're looking at the stress contours of one of the stress axes. There are three dimensions of the stress. You're looking at one of the stress axes, which is the axial direction here. And you're looking at two timestamps, 0.4 years into the life of the plug, 2 years into the life of the plug. Because this was an example case to demonstrate the workflow, I have simulated the scenario till about 2 years. There's no reason as to why we cannot really prolong the analysis. The scale is on pascals. So for example, at 0.4 years, the stress contours are ranging from close to 48 megapascal to 59 megapascal. The negative sign just indicates that the stresses are in compression. That's really all. It's a more assigned convention. I'm not showing the results of casing and cement sheet and rock here, just for simplicity. I'm focusing only on the plug portion and specifically the 1/2 plug portion. Like I said, the contours are shown only for the plug. There are two critical points of interest here that I highlighted with the dotted lines. They show the length of the propagation of the stress gradients and the stress arc that forms, connecting all the way from the bonded end of the plug, either to the casing or to the rock, depending on cased hole or open hole, to the center of the plug. Now, there is a significance for these two factors. As you can see, with time progressing, because the pore pressure is building with time at the bottom, you can see that the length of propagation of the gradients is increasing with time. Further, because of the boundary effects coming from the casing plug boundary or the rock plug boundary, depending on circumstance, there is a stress arc that forms from either end of the plug towards the center of the plug, if you can imagine. What this is telling us is that the stresses and as a consequence, the remaining capacities, if we were to calculate them for plug geometry, very much like our life analysis, the stresses in the remaining capacities are a function of space, both in the axial direction and the radial direction. These two indices will provide us insights into what is the length of the plug that is getting affected because of the loads that are getting exerted on the plug. As a consequence, we'll be able to make design decisions on the length of the plug that's required from a long-term integrity standpoint. And all of this is a function of course, the properties of the plug itself. In that sense, we can understand what are the properties of the plug. Again, to emphasize, all this treatment and the framework that I showed here is applicable for any form of plug, not necessarily plug and abandonment. So now that we are able to look at the method to design for the length and the properties of the plug, let's look at the last feature, which is cementing for the CO2 storage. Like I said, this is work in progress within technology. I want to take this opportunity to provide you a glimpse of what we are doing and also get some inputs and feedback from you. When we say the word cementing for CO2 storage, there are two aspects to the design considerations. One is that the properties of the rock will change. That happens because when you inject CO2, the CO2 will be in equilibrium with the fluid in the rock. There will be different type of ionic species, which can further interact with the reactive part of the rock and can dissolve or precipitate the rock mineralogy. As a consequence, the rock properties change. We are working with our sister PSL to understand what happens to the rock properties during the CO2 injection and how can we account for their effect in the well life analysis. I'm not going to spend my time on that part today. I'm going to spend my time on the left-hand side of the screen, which is how do the properties of cement change because of the carbonation and the bicarbonation reactions. I won't bother you with all set of reactions, but in essence, what happens is that the mineralogy of the cement changes, and as a consequence, a calcium carbonate forms, which can transform into calcium bicarbonate and can dissolve in some circumstances. And when that happens, there is a risk of leaching and of course the loss of integrity. How can we address or understand what is the relationship between these reactions, the composition, and thus the change in properties? That is the scope of the analysis and the experimentation that we are investing on. So obviously, as you can imagine, the carbonation process is a spatially varying process. I say that because the exposure happens from the rock radially inward. Whether it's a cement sheet or it's a plug, it happens radially inward. And it's a process that happens in time, which means at any point in time, there is a spatial variation of the properties. There is potentially a carbonated zone outside and an uncarbonated zone or core inside. A bulk property like strength may not give a complete picture of how the mechanical properties are because it's a bulk property and is not able to capture the surface characteristics or surface variations. From the historical test that we have done for a year-long exposure in a different context, what we were able to see is some hope that there is a potential correlation between the hardness, which is surface measurement, to the strength. So the combination of the surface measurements, bulk measurements, and chemical analysis should help us understand the relationship between the composition and the progress of the carbonation process. Our objective is to develop that framework of what is the relationship between the change in property, by property and it's a mechanical property, and to the degree of carbonation or bicarbonation. Now, the problem itself is complex because any single measurement would not help you address this challenge. You need different types of measurements which are mechanical in nature, chemical in nature. They have to come together to be able to address this challenge. So the degree of reaction itself can be tracked, estimated using different characterization techniques like XRD, thermogravimetric analysis, and the depth of penetration measurements. And the change in property, the mechanical property, can be measured using compressive strength, which is a bulk property, tensile strength, and also hardness, which are surface properties. Like I said, the calibration curve is giving us some hope that potentially we'll be able to correlate the strength and hardness. Still work in progress. So what this kind of long-term experimentation involving detailed measurements of different forms will let us do is build the relationship between the composition and the property. Once we are able to do that, we can address the question of, given a injection schedule of CO2, certain pressures and temperatures, what kind of compositions would work best in terms of delaying the process of carbonation and thus ensuring long-term integrity. So if I were to summarize the three features that I gave you an overview about, they come under a broad perspective of our intent to continue to improve the science to support the existing applications in deep water, unconventional and mature asset spaces, and further focus our development of new sciences to address challenges that are specific to the new markets of plug and abandonment and carbon storage. With that, I'd be happy to take any questions. You would have an interesting session from my colleague James Fletcher after this. Thank you.
Thank you, Siva. Hello, everyone. My name is James Fletcher. I'm a senior technical professional from Western Australia, and I'll be discussing with you the cementing solution for a carbon sequestration project that was executed for one of our customers. A little bit about the well design as a background. The well design included 9 5/8 intermediates, 7-inch drilling liner, and 4.5-inch production liner. CO2 was injected to 2 target formations perforated in the 4.5-inch liner. Tailored cement solution was executed for the 7-inch and 4.5-inch liners that was resilient to acidic attack. The acid is produced from CO2 injection, as CO2 dissolved in water produces carbonic acid, which can chemically attack the cement matrix, producing dissolvable products, which can then be whisked away by water and continuously erode your cement barrier. Halliburton approached this on 3 fronts. ISEM service is a simulation software where we can look at centralization, ECE management, among other things, which can help us with cement placement successfully. Displace 3D is a computational fluid dynamics program that uses rheological properties to simulate the placement of cement prior to execution. And that results in recommendations for continuous improvement on the rheological properties of the mud and spacer and cement, so that we can effectively displace fluids ahead and place cement efficiently. Well Life Service is a finite differential analysis software that can evaluate the stresses imposed on the cement matrix over the lifetime of the well and result in recommendations for mechanical properties improvement on the cement. CO2 resistance is imparted by the reduction of the Portland cement content, which is the component that is attacked from the acidic environment, and reduction of permeability with additives. Slurry design is a 14 ppg slurry with reduced Portland cement content. Usual cement additives including extenders, fluid loss, friction reducers, and retarders. Post-set expansion, tensile strength, and Young's modulus reduction are all mechanical properties enhancement as a result of finite differential analysis. And reduced permeability and acidic resistance is imposed by inert materials. So inert materials will occupy the space between the cement matrix and prevent molecules from the acid reaching the cement matrix and being able to chemically attack it. Well Life Service is the finite differential analysis software, which assesses the remaining capacity, which is the remaining strength under each stress regime. So 100% means that no stresses have been applied, and 0% means that the cement has failed under that stress regime. It assesses the cement under different models, which includes the curing of cement, which is the expansion or contraction as the cement sets, pressure testing, which is applying pressure to test the well, completion, which is the swap of fluids from inside, which will remove stress from the cement, production, which is the application, which is the removing pressure to flow the well, and injection, which is the application of pressure to inject CO2 in this case. So this was assessed against the injection temperature and pressure. And as you can see, the model shows that the remaining capacity is over 50% for all of the failure modes, which means that it has not failed under any of those failure modes. The failure modes assessed include plastic deformation of the casing, which is bulk deterioration, or it's bulk changes in the shape of the casing. Outer debonding, which is cement moving away from the formation. Inner debonding, which is cement moving away from the casing. Shear deterioration of cement, which is compressive strength failure. And radial cracking in cement, which is tensile strength failure from expansion. The result from the use of ISM service and Displace 3D was very good placement of cement, which was assessed by CBL, which you can see some very good examples on the right-hand side. Cement was successfully circulated after the set of each liner. You can see on the right that the result of the CBL improved over time, as the first one was CBL logged over a year after the cement was executed and put in place. And the one on the right there was CBL logged 3-4 months after. So you can see some improvement. The expansion additive over time can expand the isolation and mitigate against microannulus the longer it has to do so. So thank you very much for listening, and I will now pass the moderator for any questions that the audience may have.